Hey there, and welcome to a journey into the cosmos, a place where even death can be a spectacular new beginning. Tonight, we'll gently explore the quiet majesty of stellar afterlives, focusing on some of the universe's most incredible creations, starting with how we even came to understand the life and death of stars. But before we truly dive deep into the heart of dying stars, if you find yourself captivated by these cosmic tales, remember to like this video and subscribe to the Sleepless Scientist for more explorations. It truly helps us continue these reflective journeys, much like patiently gathering data from distant celestial objects. For millennia, across cultures and continents, humanity looked up at the night sky and saw permanence. Ancient astronomers in their quiet observatories charted the stars as eternal, unchanging lights, symbols of constancy in a shifting world. Their observations were foundational, even if their interpretations differed from ours today. They saw patterns, constellations, and the steady march of celestial bodies, assuming these luminous points in the heavens were immutable. This view of stars as fixed beacons held sway for centuries, shaping our understanding of the universe as a vast, unchanging backdrop. The idea that stars themselves had a life cycle of birth, a vibrant existence, and an eventual end was a profound shift in perspective. It required not only new tools but also a new way of thinking, a willingness to challenge deeply held beliefs about the cosmos. It wasn't until the early 20th century, with pioneering minds like Arthur Eddington, that astronomers began to truly unravel the mysteries of stellar evolution. They started to ask, what powers these distant suns, and what happens when that power fades? Imagine the patient work, hours spent at the eyepiece of a telescope, meticulously recording brightness, color, and movement. Each data point was a tiny clue, piecing together a cosmic puzzle that spanned billions of years, far beyond human comprehension. One of the most powerful tools to emerge from this era was the Hertzsprung-Russell diagram. It wasn't just a chart, it was a cosmic map, plotting a star's intrinsic brightness against its surface temperature, revealing hidden relationships. By mapping thousands of stars, astronomers could see distinct groupings and evolutionary paths. It was like looking at a forest and suddenly understanding that saplings grow into mature trees and then eventually age and change, each following a predictable pattern. This diagram showed that stars weren't static, they moved through different stages, evolving over vast timescales. It was the first clear evidence that stars had a life cycle, not just an eternal presence. But what powered this incredible journey? The answer lay deep within the star's core: nuclear fusion. It's a process where lighter elements, primarily hydrogen, are squeezed together under immense pressure and heat to form heavier elements, releasing vast amounts of energy. Think of it as a gentle, incredibly efficient furnace, burning for billions of years. This outward pressure from fusion perfectly balances the inward pull of gravity, keeping the star stable and shining brightly for most of its life. This delicate balance is what makes our sun and countless other stars such steady and reliable sources of light and warmth. It's a testament to the fundamental laws of physics playing out on a cosmic scale. However, the fuel for this furnace is not infinite. Over vast stretches of time, stars consume their hydrogen, leading to profound changes. The star begins to evolve off the main sequence of the HR diagram, signaling the beginning of its end. The most crucial factor determining a star's ultimate fate is its initial mass. It's like different seeds growing into different kinds of trees, each with its own unique lifespan and way of shedding its leaves. Smaller stars like our sun lead relatively long and peaceful lives, eventually fading into white dwarfs. But massive stars, those many times the size of our sun, follow a far more dramatic and spectacular path. These behemoths burn through their fuel at an astonishing rate, living fast and dying young by cosmic standards. Their immense gravity dictates a more energetic and violent conclusion to their existence. As a massive star fuses lighter elements into heavier ones, it progresses up the periodic table, creating elements like carbon, oxygen, and silicon in its core. Each stage of fusion generates less energy than the last. This relentless process continues until the star's core is filled with iron, and here lies the critical threshold, a point of no return. Fusing iron, unlike lighter elements, does not release energy, it consumes it. When the core becomes iron, the star can no longer generate the outward pressure needed to resist its own crushing gravity. The gentle furnace goes out, and the delicate balance is shattered in an instant. This moment marks the beginning of the end for a massive star. It's an astronomical tipping point where the forces that sustained it for millions of years suddenly turn against it, leading to an inevitable collapse. It's a truly profound realization, an object so vast and powerful, brought to its knees by a fundamental change in its very heart. This understanding opened up entirely new avenues of cosmic inquiry. Imagine a magnificent cosmic tree living for eons, its branches reaching across the galaxy, producing light and warmth. This tree, like all living things, eventually prepares for its grand farewell. For these massive stars, that farewell is not a gentle fading, but a spectacular autumn. The leaves don't just fall, they are cast off in a magnificent, violent display, enriching the universe with new elements. This dramatic conclusion, the supernova, is not just an end but a powerful beginning. It's the universe's way of recycling, of taking the ingredients forged in a star's heart and scattering them far and wide, setting the stage for new cosmic structures. And it's here, in the heart of this cosmic autumn, that our true mystery begins. The Cosmic Autumn Chapter 1 described the supernova was not always understood as such. For centuries, across various cultures, sudden brilliant guest stars would appear in the night sky. They vanished as mysteriously as they arrived, sparking wonder and fear, their true nature hidden behind their fleeting brilliance. Ancient astronomers meticulously recorded these events, noting their positions and brightness changes. They were anomalies, disruptions to the perceived eternal order of the heavens, yet their observations formed a crucial, if then misunderstood, historical record. One such event, observed in the year 1054 by Chinese astronomers, was so bright it was visible even in daylight for weeks. This guest star eventually faded, leaving behind a glowing nebula. Centuries later, we would understand this as the birth of the Crab Nebula, a stellar remnant. These historical records, though initially interpreted as new stars, hinted at something far more violent and profound. They were cosmic signposts, waiting for the right minds and tools to decipher their true meaning, a testament to the universe's quiet drama. In the mid-20th century, at Mount Wilson Observatory, two brilliant minds, Fritz Zwicky and Walter Baade, began to connect these ancient observations with new telescopic data. They were observing distant galaxies, searching for patterns in the fleeting flashes of light. They noticed certain stellar explosions were far more luminous than typical nova, outshining entire galaxies for a brief time. This led them to a radical idea. These weren't just new stars, but an entirely different class of cataclysmic event, which they termed supernova. Their theory was bold. These supernovae were the death cries of massive stars. More astonishingly, they proposed that such an explosion could leave behind an incredibly dense, compact object, a neutron star formed from the star's crushed core. This concept was revolutionary. The idea of matter compressed to such an extreme state where protons and electrons merged into neutrons was almost beyond imagination. It challenged the very limits of known physics at the time. Their hypothesis, though initially met with skepticism, provided a framework to understand the immense energy released in these cosmic events. It was a leap of intuition, grounded in the careful analysis of observed phenomena and theoretical possibilities. Over time, as more evidence accumulated from observations and particle physics, the concept of a neutron star gained traction. It became clear that Zwicky and Baud had glimpsed a profound truth about the universe's most extreme conditions. Returning to the heart of the dying massive star, Chapter 1 left us with an iron core, no longer able to produce energy through fusion. Without this outward pressure, the star's immense gravity suddenly becomes unopposed, triggering a catastrophic collapse. This is not a gentle inward sigh, but a violent, rapid implosion. The core, once supported by fusion, now falls inward at speeds approaching a quarter of the speed of light, shrinking from Earth size to city size in mere milliseconds. The densities reached during this collapse are almost inconceivable. Imagine all the matter of every car on Earth crushed into a single sugar cube. That begins to approach the density of this collapsing stellar core. As the core compresses, its constituent atoms are squeezed beyond recognition. Electrons are forced into protons, creating neutrons and releasing a flood of ghost-like particles, neutrinos. The core becomes an incompressible, superdense ball of neutrons, essentially a giant atomic nucleus. The inward fall of matter is suddenly, violently halted as the core bounces back, creating a powerful shock wave. During this extreme compression, an incredible burst of neutrinos is released. These elusive particles interact very weakly with matter, so they stream out from the collapsing core, carrying away vast amounts of energy. This neutrino burst is a silent, ghostly whisper from the dying star's heart, a momentary glimpse into the most extreme physics. Detecting these neutrinos on Earth is a monumental task, but it offers direct evidence of the collapse. The shockwave generated by the core's rebound begins its journey outward, tearing through the star's outer layers. This is the mechanism that powers the spectacular explosion we see as a supernova. As the shockwave propagates, it heats and compresses the stellar material, triggering rapid nuclear reactions. This creates elements heavier than iron, such as gold, silver, and uranium, forging them in the furnace of destruction. These newly forged elements, along with the star's original outer layers, are then violently ejected into space. This cosmic scattering enriches the interstellar medium, providing the building blocks for future stars, planets, and even life itself. The supernova is a vast, slow-motion cosmic exhale. It's the universe releasing a lifetime of accumulated energy and material, not in a destructive act, but as a peaceful, profound redistribution. The light we see from a supernova is the brilliant, fleeting signature of this grand exhalation. For weeks or months, it can outshine entire galaxies, a beacon marking the end of one cosmic journey and the beginning of countless others. The heavy elements found in our own bodies and on our planet, the iron in our blood, the gold in our jewelry, were all forged in the hearts of massive stars and scattered across the cosmos by these very explosions. Without supernova, the universe would be a much simpler place, devoid of the chemical complexity needed for planets and living organisms. They are the ultimate cosmic recyclers, turning death into the raw material for new creation. But what remains after such a magnificent farewell? What compact, incredibly dense object is left behind at the heart of this cosmic exhale? That is the quiet, profound mystery we will delve into next, uncovering the universe's most extreme remnants. After the supernova's brilliant farewell, a profound silence descends. The vast stellar material, once a star's vibrant body, is now cast wide, but at the very heart of that cosmic exhale, something remains. A core, impossibly dense, yet still struggling against the relentless grip of gravity, continues its desperate inward journey. For a brief, terrifying moment, it seemed nothing could halt this collapse. The core, once the size of Earth, was now shrinking at incredible speeds. The forces at play were beyond anything encountered in our everyday world, pushing the very fabric of matter to its absolute limits. The pressure within this shrinking remnant reached truly unimaginable levels. Every atom was squeezed, its electrons and protons packed tighter and tighter. It was a cosmic vise, relentlessly crushing the very building blocks of matter. Scientists, long before any direct observation, theorized about such extreme states. They pondered, what happens when atoms are no longer distinct entities? What new forms could matter take under such overwhelming duress? Deep within that collapsing core, a remarkable transformation began. The immense pressure forced electrons and protons together, overcoming the electromagnetic repulsion that normally keeps them apart. It was a fundamental shift, orchestrated by gravity's ultimate power. This was not a violent collision, but a peaceful, almost elegant merging. Under such conditions, protons absorbed electrons, quietly transforming into neutrons, releasing a flood of ghostly neutrinos that streamed effortlessly away. The core rapidly became a vast, uniform sea of neutrons, no longer individual atoms but a single, giant atomic nucleus held together by the strong nuclear force. This new state of matter was unlike anything found on Earth. And then, a new force emerged to finally resist gravity's relentless pull: neutron degeneracy pressure. It's a quantum mechanical effect born from the Pauli exclusion principle, which states that no two identical neutrons can occupy the same quantum state. Imagine trying to fit too many identical marbles into a very small box. They will resist being pushed closer, not because they are solid, but because the rules of their existence prevent them from occupying the same space in the same way. This is a simplified analogy for degeneracy pressure. This incredibly powerful, repulsive force arising from the neutron's refusal to be further compressed finally provided the counterbalance. It was the ultimate, unyielding wall against gravity's insatiable hunger. The collapse, which had seemed unstoppable, was suddenly, violently halted. The inward rush of matter slammed against this impenetrable neutron barrier, creating a new, stable, yet incredibly compact object. This was the birth of a neutron star, a stellar remnant, perhaps only 20 kilometers across, yet containing more mass than our entire sun. It was an impossibly small, incredibly dense world, forged in the fires of a supernova. Think of it like a collapsing sandcastle, but instead of simply turning to dust, the entire castle gently transforms into a single, impossibly dense, sparkling grain of sand. This tiny grain holds the original mass, yet is now in an entirely new, extreme state. The existence of such an extreme object was theorized decades before any observation. As early as 1932, the brilliant Soviet physicist Lev Landau, just after the discovery of the neutron, proposed the idea of neutron stars. Later, in 1939, J. Robert Oppenheimer and his student George Volkoff meticulously worked out the theoretical structure of these objects. Their equations described a star unlike any known, one where gravity was balanced by this exotic neutron degeneracy pressure. Their predictions were met with a mix of awe and skepticism. The idea of matter so compressed that a teaspoonful would weigh billions of tons was almost science fiction. It pushed the boundaries of what was considered possible in the cosmos. Yet the theoretical framework was elegant and consistent. It provided a logical endpoint for the collapse of massive stars, explaining where the immense gravitational energy could be finally resisted. It was a triumph of theoretical physics. For years, these neutron stars remained purely theoretical constructs, existing only in the minds of scientists and on the pages of equations. They were a cosmic hypothesis, waiting for the universe to confirm their existence. Imagine contemplating an object where the entire population of humanity, if compressed, would fit into a single raindrop. This was the scale of density they were predicting, a truly mind-bending concept. The quiet pursuit of understanding, driven by pure curiosity, led these scientists to envision these extreme cosmic entities. They built a framework for a universe far stranger and more wonderful than previously imagined. This nascent neutron star, born from the spectacular death of a giant, was a new world entirely. Not a world of gas or rock, but a world of pure nuclear matter, held in a delicate, yet incredibly strong, balance. Its formation marked the end of one cosmic chapter and the quiet beginning of another, a testament to the universe's ability to transform destruction into creation, leaving behind a silent, powerful legacy. This cosmic diamond, incredibly small yet profoundly significant, now drifted through the void. It was a relic, a monument to the extreme physics that govern the most massive stars. But how would we ever find such an object? How would humanity, from its distant perch, eventually detect these theoretical behemoths silently orbiting through the galaxy? The answer lay in their unique, energetic signatures. The birth of a neutron star was only the first step in understanding these enigmatic objects. Its subsequent life, its incredible rotation, and its powerful magnetic fields would soon reveal themselves, through the patient listening of distant instruments, in ways no one could have fully predicted. The neutron star, born from the spectacular collapse, was a theoretical marvel. Scientists, with their elegant equations, began to probe its impossible interior, a realm where matter was compressed beyond anything imaginable. It was a world entirely new, demanding new physics. Imagine taking all the material of a massive mountain, say Mount Everest, and squeezing it down to the size of a single sugar cube. This thought experiment, often shared among physicists, helps grasp the sheer, mind-bending density of a neutron star. This extreme state of matter, where a teaspoonful could weigh billions of tons, was not just a curiosity. It was a cosmic laboratory, offering insights into the fundamental forces that govern the universe under conditions impossible to replicate on Earth. Despite its minuscule size, a neutron star is not uniform. Theoretical models, painstakingly developed over decades, suggest a layered structure, much like an onion, each layer holding its own peculiar physics and secrets. The outermost layer, a mere few meters thick, is thought to be a solid, crystalline crust. Here, the remaining protons and electrons, along with some neutrons, form a rigid lattice, held together by immense gravitational forces. This crust is not like any rock we know. It's an electron gas permeating a lattice of atomic nuclei, mostly iron, but crushed so tightly that it's far stronger than steel, making it the strongest material in the universe. Below this incredibly tough crust lies the outer core, a fluid region primarily composed of neutrons. But this is no ordinary fluid. It is believed to be a superfluid, a state of matter with astonishing properties. Superfluidity means it flows without any friction. Imagine a liquid that, once set in motion, would swirl forever without losing energy. This frictionless movement is a bizarre consequence of quantum mechanics operating on a macroscopic scale. This superfluid neutron matter would behave in ways entirely alien to our experience, potentially creating quantized vortices within the star, influencing its rotation and magnetic field in subtle, profound ways. And perhaps even more astonishingly, this superfluid might also be a superconductor. This means it could conduct electricity with zero resistance, allowing electric currents to flow indefinitely without energy loss. Such superconductivity within the neutron star's core could be responsible for generating and sustaining the incredibly powerful magnetic fields that these objects are known to possess, fields billions of times stronger than Earth's. Beyond the internal structure, the sheer density of a neutron star profoundly warps the fabric of spacetime around it. Einstein's theory of general relativity predicts that mass tells spacetime how to curve, and spacetime tells mass how to move. For a neutron star, this warping is profound, yet remarkably contained. It's a gentle, deep indentation in the cosmic fabric, pulling light and time into its gravitational embrace, but without the absolute finality of a black hole. Light passing close to a neutron star is bent so severely that we can, in theory, see parts of its far side. It's like looking around a corner, a testament to gravity's quiet, powerful influence on light's path. But the deepest mysteries lie at the very heart of the neutron star, its inner core. Here, the pressures are so extreme that even neutrons might be crushed, leading to a theoretical state of matter known as quark matter or strange matter. Quarks are the fundamental particles that make up protons and neutrons. At these unimaginable densities, it's hypothesized that neutrons might dissolve, allowing their constituent quarks to roam freely, forming a sea of elementary particles. This quark-gluon plasma would be a relic of the early universe, a state of matter that existed only moments after the Big Bang. Discovering it within a neutron star would be a profound validation of our understanding of fundamental physics. The quest for strange matter is an ongoing theoretical endeavor, pushing the boundaries of what we know about matter itself. It's a frontier where nuclear physics meets astrophysics, seeking to understand the ultimate limits of compression. Within this extreme environment, another surprising prediction emerged. Sound could travel at nearly the speed of light. In such a rigid, incompressible medium, disturbances propagate with astonishing swiftness. This is not sound as we know it, but a theoretical propagation of pressure waves, a whisper from the core moving with a speed that approaches the ultimate cosmic limit. The internal dynamics of a neutron star are a symphony of extreme physics, a delicate balance of forces, and a testament to matter's resilience under unimaginable stress. It is a cosmic marvel. Imagine a vast, tranquil ocean with all its deep currents and hidden wonders compressed into a single, perfect dewdrop. Yet within that dewdrop, all the profound depths and internal movements of the ocean are retained. This analogy helps us grasp the neutron star, a tiny, silent world yet teeming with incredible internal activity, a microcosm of extreme physics quietly unfolding in the vastness of space. The theoretical understanding of these impossible densities laid the groundwork for future discoveries. It allowed scientists to predict the observable signatures of these hidden cosmic gems, guiding the search. And it was these very signatures, the intense gravity, the powerful magnetic fields, and especially their incredible spin, that would eventually betray their presence to patient listeners across the galaxy, revealing them not as silent monoliths but as cosmic lighthouses, beaming their secrets across the void. The universe whispered secrets, but to hear them, humanity needed new ears. In the mid-20th century, these ears were vast arrays of metal, patiently listening for faint radio waves from the cosmos, hoping to catch the subtle signatures Chapter 4 alluded to. These radio observatories were designed to capture the invisible, to translate cosmic energies into decipherable signals. It was a painstaking endeavor, sifting through the constant hum of the universe and the ever-present terrestrial interference. In the late 1960s, at the Mullard Radio Astronomy Observatory in Cambridge, a new, massive radio telescope array was taking shape. Its purpose was to study quasars, distant, energetic galaxies, by observing how their radio signals twinkled through the interstellar medium. A young postgraduate student, Jocelyn Bell Burnell, was tasked with analyzing the reams of data pouring from this new instrument. Her role was crucial, a quiet sentinel watching over the cosmic signals, each one a potential clue. The data wasn't digital in the modern sense, it was recorded on long paper charts, unwinding from giant spools. Hours were spent meticulously scanning these charts, searching for patterns, for anything that deviated from the expected cosmic background. Day after day, week after week, the charts flowed. Most of it was noise or predictable cosmic murmurs. Until one day in August 1967, a tiny, persistent signal appeared, a faint, rhythmic scruff on the otherwise familiar trace. This signal was unlike anything seen before. It pulsed with astonishing regularity, a steady beat every 33 seconds, unwavering, precise. It was too regular to be terrestrial interference, too consistent to be random cosmic static. Initially, the team, including her supervisor Anthony Hewish, suspected a local disturbance, perhaps a faulty piece of equipment or a passing truck, but repeated checks confirmed it. The signal was coming from beyond Earth. They systematically ruled out known celestial phenomena. Stars, galaxies, nebulae, none produced such incredibly precise, rapid pulses. The mystery deepened with each eliminated possibility, pushing them into uncharted territory. In a moment of playful speculation, the team humorously nicknamed the source LGM-1 for Little Green Men. It was a lighthearted acknowledgement of just how baffling this entirely new phenomenon was, a nod to the unknown. But beneath the jest lay the rigorous scientific imperative to find a natural, astrophysical explanation. The universe, though full of wonders, rarely resorted to such direct, artificial signals, demanding a deeper understanding. Further observations confirmed the signal was indeed extraterrestrial, originating from a fixed point in the sky, moving with the stars. This was not a local anomaly, it was a cosmic message, albeit one still awaiting translation. The real breakthrough came when Bell Burnell discovered a second, then a third, and finally a fourth similar pulsing source, each with its own unique, incredibly precise period, but all exhibiting the same rhythmic character. This proliferation of signals made the Little Green Men hypothesis untenable. The universe wasn't sending a coordinated message. It was revealing a new class of object, a previously unimagined cosmic entity, quietly announcing its presence. The incredible regularity and rapid pulsing hinted at something small, dense, and rapidly rotating. The only known theoretical objects that fit this description were the neutron stars, envisioned decades earlier as the remnants of supernova. The elegant solution proposed by Hewish and Bell Burnell became known as the lighthouse model. Imagine a rapidly spinning neutron star emitting powerful beams of radio waves from its magnetic poles. As this cosmic lighthouse spins, its beams sweep across our line of sight, much like a terrestrial lighthouse beam sweeps past a ship at sea. Each time a beam crosses Earth, we detect a precise pulse of radio energy. For these pulses to be so rapid, the neutron star itself must be spinning at astonishing speeds, sometimes hundreds of times per second. This rapid rotation is a remnant of the star's collapse, conserving its immense angular momentum. These newly discovered objects were christened pulsars, a contraction of pulsating radio sources. A new chapter in astrophysics had begun, confirming the existence of Zwicky and Bod's theoretical remnants, now revealed as cosmic beacons. The precision of pulsar timing is extraordinary. Some pulsars are more accurate than atomic clocks on Earth, making them invaluable tools for probing the universe's most fundamental laws. Their unwavering rhythm allows scientists to test Einstein's theory of general relativity with exquisite precision, observing how their pulses are subtly affected by the spacetime curvature around them or by the presence of other massive objects. The discovery of binary pulsars, two neutron stars orbiting each other, provided indirect evidence for gravitational waves, a prediction of general relativity, long before their direct detection. These cosmic dances revealed the universe's subtle ripples. These silent cosmic beacons, born from violent stellar deaths, now offer a rhythmic pulse across the vastness of space. They are the universe's quiet metronomes, marking time and revealing hidden truths about its most extreme physics. Imagine a distant, benevolent cosmic beacon silently guiding us through the universe's vastness with its unwavering, rhythmic pulse. It's a reminder of the deep order that underlies the cosmic chaos, a gentle beat in the quiet expanse. Pulsars unveiled the incredible nature of rotating neutron stars, but some of these remnants hold even more extreme secrets. Their magnetic fields, in particular, can reach intensities that defy imagination, leading to phenomena even more dramatic than a rhythmic pulse, phenomena that will pull us into a realm of truly unimaginable power. Chapter 5 unveiled the rhythmic whispers of pulsars, neutron stars spinning with incredible precision, their powerful magnetic fields sweeping beams of radio waves across the cosmos. But some of these stellar remnants held secrets of an even more profound intensity, their magnetic fields reaching magnitudes that defied imagination, quietly shaping extreme phenomena. As the 1990s dawned, astronomers using new generations of X-ray and gamma-ray telescopes began to detect peculiar, high-energy bursts from deep space. These events were distinct from the more well-understood phenomena, hinting at a new cosmic puzzle that required careful observation and fresh theoretical insights. One class of these perplexing signals was named soft gamma repeaters, or SGR. They were characterized by short, intense bursts of gamma rays, but unlike typical one-off gamma ray bursts, these events recurred, sometimes many times over years, from the same points in the sky. The soft in their name referred to the lower energy of their photons compared to other gamma-ray bursts. This subtle difference was a crucial clue, suggesting a distinct physical mechanism at play, one that didn't fit neatly into existing models of stellar explosions. What made SGRs even more intriguing was their celestial location. They were often found within supernova remnants or near star-forming regions, places where the violent deaths of massive stars would naturally lead to the birth of neutron stars. Simultaneously, another group of mysterious objects emerged, anomalous X-ray pulsars, or AXP. These were neutron stars that emitted X-rays in a steady, rhythmic pulse, much like radio pulsars, but with a crucial difference. AXPs spun much slower than typical radio pulsars, and their X-ray emissions were too powerful to be explained by their rotational energy alone. Crucially, there was no sign of a binary companion star to feed them with gas, ruling out accretion as their power source. Here was a cosmic conundrum: two distinct types of objects, SGR and AXP, both linked to neutron stars, both emitting intense, high-energy radiation, yet both lacking a clear, conventional explanation for their energetic output. The universe was presenting a new mystery. The existing theoretical models for neutron stars, which beautifully explained radio pulsars, struggled to account for these anomalies. The sheer power and the unique characteristics of SGRs and AXPs demanded a more extreme explanation. Into this perplexing landscape stepped two pioneering theorists, Robert Duncan and Christopher Thompson. Working independently and then collaboratively, they began to piece together a radical new hypothesis in the early 1990s. Their idea was audacious. What if these weren't just ordinary neutron stars, but magnetars, neutron stars endowed with magnetic fields so incredibly powerful that they dwarfed anything else in the cosmos, becoming the dominant force in their existence? The scale of these proposed magnetic fields was mind-boggling. Quadrillions of times stronger than Earth's magnetic field, they were so intense they could rip apart atoms or distort light itself. A magnetar would instantly erase the data on every credit card on Earth from a distance of 100,000 miles. The theoretical understanding of how such immense magnetic fields could originate was crucial. It was thought that the extreme conditions within a newly formed neutron star, particularly its rapid rotation and convection of its fluid interior, could amplify a seed magnetic field to incredible strengths. This magnetorotational dynamo process, occurring in the turbulent, perhaps even superfluid and superconducting, core of the nascent neutron star, would twist and stretch magnetic field lines, locking in immense magnetic energy. For magnetars, it was the decay of this colossal magnetic field that provided the energy for their spectacular emissions. As the field lines twisted, snapped, and reconnected, they released vast amounts of energy in the form of X-rays and gamma rays. This mechanism beautifully explained the SGRs. The sudden, intense gamma-ray bursts were interpreted as magnetic flares, rapid, violent reconfigurations of the magnetar's external magnetic field, much like solar flares, but on an incomparably grander scale. The AXP, with their slower, steady X-ray pulsations, were also accounted for. The gradual decay and twisting of the internal magnetic field would heat the neutron star's crust, causing it to emit X-rays over long periods without needing external fuel. Sometimes, the immense stress of these magnetic fields could cause the neutron star's incredibly strong crust to crack, much like an earthquake on Earth. These starquakes would release enormous amounts of energy, manifesting as powerful flares. These magnetar flares could be so energetic that, even from thousands of light years away, their radiation could briefly affect Earth's ionosphere. They were cosmic adjustments, ripples of power propagating outwards from a distant, magnetic heart. Despite their colossal power, these starquakes and flares were, in a cosmic sense, gentle adjustments. The magnetar was not collapsing or exploding, it was simply settling, its immense internal magnetic stresses finding new, temporary equilibria. Imagine a calm, deep lake. Its surface appears tranquil, unmoving, but unseen beneath, powerful, deep currents flow, occasionally causing a ripple to break the surface, a fleeting sign of the immense, hidden forces at play within. This analogy helps us understand magnetars. They are profoundly tranquil in their existence, not violently unstable. The magnetic field, like the deep current, is an unseen force that occasionally expresses itself through powerful, yet contained, cosmic adjustments. The realization of magnetars as a distinct class of neutron stars was a triumph of theoretical prediction and observational confirmation. It expanded our understanding of extreme matter and the fundamental forces that govern the universe. These magnetic monsters, far from being chaotic, were simply another facet of the neutron star's incredible versatility. They are cosmic laboratories where magnetism reigns supreme, offering unique insights into the most extreme physics imaginable. As we continue to observe these gentle giants of magnetism, new questions arise. How do these fields evolve over cosmic timescales? What happens when two such extreme objects meet? And what other profound yet quiet roles do they play in the ongoing cosmic narrative? Chapter 6 explored the solitary, intense world of magnetars. Yet many neutron stars do not drift alone. They are often found in intimate cosmic partnerships, locked in gravitational embraces with companion stars, revealing even more profound dynamics. The discovery of these binary systems began with a new window to the universe, X-ray astronomy. In the 1970s, as satellites like Uhuru launched, they started to map the high-energy sky, searching for new sources of radiation. These new instruments allowed scientists to observe phenomena invisible to optical telescopes. They were designed to capture the energetic whispers of the cosmos, hinting at processes far more violent than gentle starlight. Soon, mysterious, intensely bright X-ray sources were detected. Unlike steady stars, their emissions varied dramatically, often in predictable cycles, suggesting something was orbiting something else with immense gravity. The puzzle was solved when these X-ray sources were correlated with known stars. It became clear a compact object, an unseen companion, was drawing material from a visible star, emitting X-rays as it did so. This compact object was, in many cases, a neutron star. Its immense gravitational pull gently siphoned gas from its larger, less dense companion, creating a celestial dance of matter transfer. As the gas spiraled inward, it did not fall directly onto the neutron star. Instead, it formed a vast, flattened disk known as an accretion disk, slowly swirling around its dense partner. Within this disk, friction heated the gas to millions of degrees, causing it to emit copious amounts of X-rays. It was a peaceful yet powerful transfer of energy, a cosmic ballet of matter and gravity. Occasionally, these systems would flare up in what are known as X-ray bursts. These were not violent explosions, but rather gentle, energetic outbursts lasting only seconds, yet incredibly bright. These bursts occur when hydrogen and helium accumulate on the neutron star's surface. When enough material builds up, it ignites in a thermonuclear flash, briefly outshining the entire system. Another fascinating phenomenon observed in these binaries was the existence of millisecond pulsars. These are neutron stars spinning hundreds of times per second, far faster than typical pulsars. The incredible speed of these pulsars is believed to be the result of a spin-up process. The infalling matter from the companion star transfers its angular momentum, gradually accelerating the neutron star over millions of years. It's a subtle yet profound interaction where the gentle trickle of gas from one star can transform its compact partner into one of the fastest rotating objects in the universe, a testament to the power of persistent, quiet forces. While X-ray astronomy revealed the elegant dances of matter, a new frontier in the 21st century opened our ears to an even deeper cosmic symphony: gravitational waves. The Laser Interferometer Gravitational Wave Observatory, or LIGO, along with its European counterpart Virgo, was designed to detect the subtle ripples in spacetime caused by the most violent events in the universe. For decades, these observatories patiently listened, searching for a signal so faint it could only be caused by truly cataclysmic cosmic events, a whisper from the fabric of reality itself. Then, in August 2017, came the groundbreaking detection, GW 170,817. It was the signal of two neutron stars locked in a final, accelerating spiral merging into one. The gravitational wave signal was followed almost immediately by a flash of light, visible across the electromagnetic spectrum. This was the kilonova event, a direct confirmation of the merger. This kilonova provided crucial evidence. The intense conditions during the merger of two neutron stars were the perfect cosmic forge for heavy elements. It confirmed that these mergers are the primary source for elements heavier than iron, such as gold, platinum, and uranium, scattering them across the universe, enriching the cosmic tapestry. Imagine two celestial dancers orbiting each other in a slow, elegant waltz. Their gravity creates a gentle, beautiful cosmic ballet, drawing them closer and closer over eons. This dance, though seemingly peaceful, culminates in a final, powerful embrace. A moment of immense energy, yet one that quietly creates the most precious elements in the universe, shaping the very composition of planets and life. The gold in our jewelry, the platinum in our technology, the uranium that fuels our power, all forged in these incredible, distant mergers. Our very existence is tied to these cosmic dances. Neutron stars, whether solitary or in harmonious binaries, are profound laboratories of extreme physics. They are quiet architects of the cosmos, recycling matter, forging elements, and sculpting the universe in ways we are only beginning to comprehend. As we continue to listen, to observe, and to piece together these cosmic stories, the full, peaceful significance of neutron stars in the grand narrative of the universe slowly unfolds, leading us to ponder their ultimate, quiet fate and their enduring legacy across the vastness of time. The quiet legacy of neutron stars, those impossibly dense remnants, extends far beyond their individual existence. They are not merely endpoints of stellar evolution, but active participants, shaping the universe in profound, often subtle ways, as Chapter 7 hinted. These compact objects, forged in supernova fires, serve as the universe's ultimate laboratories. Within their extreme cores and in their intense gravitational fields, the very laws of physics are tested under conditions unimaginable on Earth, pushing our understanding to its limits. Scientists meticulously design experiments on Earth, but nothing can truly replicate the crushing pressures and densities found within a neutron star. They are cosmic benchmarks, offering natural experiments that transcend our terrestrial capabilities. For instance, their incredible gravity allows us to test Einstein's theory of general relativity with exquisite precision. The subtle bending of light and the warping of spacetime around them provide real-world data for our most fundamental theories. Every pulse from a distant pulsar, every gravitational wave ripple from a merger, offers a data point in this grand cosmic experiment. It's a patient, ongoing process of observation and theoretical refinement, pushing the boundaries of knowledge. The extreme conditions also probe the very nature of nuclear matter, far beyond what accelerators on Earth can achieve. They are windows into the behavior of quarks and gluons, the fundamental particles that make up matter. Imagine a microscopic probe pushed into the heart of an atom, revealing its innermost secrets. Neutron stars are like that, but on a cosmic scale, naturally dissecting matter's ultimate structure for us to decipher. The implications of these tests are profound, affecting our understanding of gravity, quantum mechanics, and the strong nuclear force. They help us build a more complete picture of the universe's fundamental architecture. Our journey through stellar life cycles has shown us that supernova explosions forge elements up to iron, but the heaviest elements, like gold and uranium, find their quiet genesis in neutron star mergers, as we saw in Chapter 7. These cosmic cataclysms, though violent, are ultimately acts of creation. They are the universe's alchemists, transforming simple elements into the complex building blocks necessary for planets and life. Every atom of gold on Earth, every trace of platinum in our devices was once forged in the heart of a neutron star merger, scattered across the cosmos and eventually gathered into our solar system. We are literally stardust. Without these extreme events, the cosmic tapestry would be far less rich, lacking the chemical diversity that makes our world, and indeed our very existence, possible. They are quiet, powerful enrichers of the universe. The patient observation of kilonovae, the luminous aftermath of neutron star mergers, directly confirms this. We are witnessing the birthplaces of the universe's most precious elements, unfolding in slow motion across light years. Beyond forging elements, neutron stars also act as powerful accelerators. Their rapidly spinning, highly magnetized environments can propel charged particles to incredible speeds, creating what we know as cosmic rays. These cosmic rays, high-energy particles traveling near the speed of light, constantly bombard Earth. Their origins have long been a mystery, but neutron stars are emerging as significant contributors to their acceleration. Imagine them as gentle cosmic seeds scattering these high-energy particles across the galaxy. These particles can then interact with interstellar gas, leading to further nuclear reactions and enriching the cosmic environment. The study of cosmic rays through ground-based and space-based detectors allows us to trace these energetic messengers back to their powerful sources, revealing another quiet yet profound role of neutron stars. The elusive nature of dark matter remains one of cosmology's greatest puzzles. Intriguingly, neutron stars offer a unique arena to search for its subtle interactions, acting as dense cosmic traps or probes. If dark matter particles interact, even weakly, with ordinary matter, they could accumulate within the incredibly dense core of a neutron star. This accumulation could subtly affect the star's properties, offering a detectable signature. Scientists are developing innovative theories and observational strategies to look for these faint signals. It's a testament to human ingenuity, using the most extreme objects to hunt for the most elusive particles. This research transforms neutron stars into natural particle detectors, leveraging their extreme conditions to explore physics beyond the standard model. They become silent sentinels in the hunt for dark matter. Ultimately, these extreme objects are vital for refining our understanding of the equation of state for nuclear matter. This fundamental equation describes how matter behaves under immense pressure, dictating the very fabric of reality within a neutron star. The equation of state is crucial for predicting a neutron star's mass-radius relationship, its internal structure, and its maximum possible mass. Every new observation helps to constrain and refine this critical piece of physics. It's a continuous dance between theory and observation, where the universe provides the ultimate testbed for our most profound ideas about matter and gravity. Neutron stars are the quiet arbiters of these fundamental truths. Like silent ancient sculptors working in the deepest cosmic studios, neutron stars quietly shape the very elements that make up our world and ourselves. Their enduring legacy is etched into the universe's fabric, a testament to creation born from stellar death. Yet even these architects face an ultimate fate, a final chapter in their cosmic story, which continues to unfold for us to discover. Even after decades of study, neutron stars hold deep secrets. The precise nature of the exotic matter within their cores, for instance, remains one of astrophysics' most profound puzzles. What truly lies beneath that incredibly tough crust? Our models offer glimpses, but direct understanding is elusive. Then there are their colossal magnetic fields, billions of times stronger than Earth's. The exact mechanisms of their origin and how they evolve over cosmic timescales are still subjects of intense research, demanding a blend of theory and observation. And the enigma of pulsar glitches, sudden, unpredictable speed-ups in their incredibly precise rotation. These tiny cosmic tremors offer a unique window into the superfluid interior of neutron stars, hinting at dynamic processes hidden from our direct view. But new instruments are rising, promising deeper insights. The Square Kilometre Array, a vast network of radio telescopes spanning continents, will offer unprecedented sensitivity to these faint cosmic whispers. Its sheer power will allow us to detect even fainter pulsars, to track their subtle changes, and to map their magnetic fields with exquisite detail, revealing new facets of their peaceful yet profound existence. Next-generation gravitational wave observatories, more sensitive than their predecessors, promise to map the universe's ripples with even greater clarity, catching the quiet echoes of neutron star mergers from further away. These new ears will allow us to hear the final, gentle embrace of these cosmic dancers, providing richer data on the heavy elements they forge and the extreme physics they embody in their ultimate moments. These stellar afterlives offer profound philosophical reflections. They remind us of the universe's quiet yet immense capacity for transformation, turning destruction into new forms of being. From violent beginnings comes quiet, enduring stability, a testament to nature's grand cycle where nothing is truly lost, only changed, recycled into the building blocks of new worlds and life. Neutron stars are unique bridges. They connect the incredibly small realm of particle physics, probing the behavior of quarks and gluons, to the vastness of cosmology, influencing the distribution of elements across galaxies. Their extreme conditions test the very limits of our theories, revealing how fundamental forces operate on both the tiniest and grandest scales, unifying our understanding of the cosmos. This quest for understanding is driven by an enduring human curiosity. Our calm, persistent desire to decipher the universe's most extreme phenomena is a quiet force, pushing the boundaries of knowledge. It is a journey of patience, meticulous observation, and the occasional breathtaking breakthrough. Each discovery, each answered question, opens new avenues for inquiry, like a quiet river carving its path through stone. Imagine a peaceful, flowing river of knowledge. Each neutron star is like a reflective stone within this river, revealing deeper insights into the universe's enduring, tranquil mysteries, inviting endless contemplation. They are cosmic laboratories, testing the very fabric of spacetime and matter under conditions we can only dream of replicating on Earth. They hold the keys to understanding gravity's ultimate power. The collaborative, global scientific endeavors of today, linking observatories and minds across continents, are slowly, patiently unraveling these intricate cosmic threads. Every careful calibration, every hour of data analysis contributes to this vast, shared tapestry of knowledge. It is a quiet, collective effort to listen to the universe's most subtle whispers. The journey to understand neutron stars is a microcosm of science itself, a persistent, often quiet pursuit of truth driven by an insatiable wonder at the universe's design. They are the universe's silent architects, forging the elements of life, testing the laws of physics, and forever challenging our perceptions of reality and possibility. Our understanding grows not with shouts but with patient whispers, with the steady accumulation of evidence, and with the courage to imagine what lies beyond the known. The profound beauty of these objects lies not just in their extreme nature, but in the quiet, enduring role they play in the cosmic narrative, shaping the universe in ways we are only beginning to truly appreciate. They are a testament to the universe's elegance, where death is a spectacular, creative force, and the remnants continue to influence the cosmos for eons. This ongoing exploration reminds us that the universe is a place of endless, gentle wonder, always inviting us to look a little closer, to listen a little more attentively. And as we continue our journey, these quiet cosmic architects continue their silent work, shaping the universe, inviting us to forever ponder their profound, peaceful existence. Their story, like the universe itself, is one of endless transformation, a quiet, powerful dance of creation and legacy. And so, as the moon climbs high, sleep well, knowing the universe holds endless, gentle wonders.